delayed reading. This is the design and verification issues in 2024. What have we been reading over the past years? Over the past year, this often indicated the problems you most desperately need to be solved. At the end of this year, I look back over the story published and those that top 13 terms of the leadership. I concentrated those stories are about the EDA tools and flows, the factors that are influencing it. These are good indicators of the problems the designers and verification teams are facing today and where they are looking for. So this year's leading category are fundamental changes with the EDA, power, thermal, and efficiency issues, chiplet, and memory. With those categories, stories that deal with the design side of issue tend to get more readers than those that deal with the verification by about 30%. I have never quite worked out why this is the case, given that the verification engineers outnumber designers in many companies. The half the verification engineers are just too busy. I would love to hear your views about this. So the fundamental changes with the EDA over the past new years, EDA has been stretched thin. Not only have it been racing to deal with the new technology nodes and introduction of the new packages option, but at the high end, the more systems-centric side of demand. I wrote the top story of the year just a couple of months ago. Shift left is the tip of the iceberg on the surface. Shift left may look like a minor change in bar window major strategy or the introduction of the new metrics, but this is a fundamental move from an insurance my conduct perspective, the start of the system's age of design. A surprising top story was, is there any hope for asynchronous design? Is an era when power has become a fundamental design constraint? Question persists about whether the asynchronous logic has a role to play. It is the design style said to have a significant efficiency and yet has never resulted in more than a few experiments. Looking at the industry in general, the Eddie Spaulding wrote, "There looks beyond chips." Top EDA executives have been talking about expanding into agent markets for more than a decade. But the broader market were largely closed to them. In fact, the only significant step in that space happened in the reverse direction when Siemens bought Mental Graphics in 2016 for $5 billion. Three things have been changed fundamentally since then. There have been several announcements about the usage of the AI within the EDA. Karen Heyman wrote to AI's role in the design widens drawing in the startups. The using AI in EDA is invigorating the whole tools industry, promoting the established players to upgrade their tools offering with the AI ML features, while joining the startup is trying to carve out differentiated approaches to fulfill unaddressed gaps to new tools and methodologies. Finally, in this category, I wrote, will AI disrupt the EDA? Generative AI has disrupted search. It is transforming the computing landscape, and now it's threatening to disrupt the EDA. But despite the buzz and the broad pronouncement of the radical changes ahead, it remains unclear where it will have impact and how deep any changes will be. Power, thermal, and efficiency. An increasing number of designers are power-conscious design. There is no longer just a domain of battery-operated devices. Ed Spaulding topped this category, writing about the rising price of power in chips. Transistor density has reached a point where these tiny digital switches are generating more than can be removed through the traditional means. That may sound manageable enough, except it has created a slew of the new problems that require the entire industry to solve. EDA companies, process equipment makers, fabs, packaging houses, field level monitoring and analytic providers, material suppliers, research groups, and etc. A lot of people are concerned about design for data centers, and most theorists wrote down the architecture for high-performance computing. The world leading high Hyperscaler cloud data center companies are launching heterogeneous multi-core architectures specifically for the cloud, and the impact is being felt in the high-performance CPU development across the chip industry. So the performance per watt is become the new optimization criteria at spelling the road a new AI processors architectures balance speed with efficiency. Leading AI systems designers are migrating away from the building the fastest AI processor possible or adopting a more balanced approach that involves the high specialized heterogeneous compute elements, so the faster data movement and significantly lower power. Chiplet. Heterogeneous integration has become the more commonplace, but the industry has still not solved all of the problems necessary for the third-party chiplet market to develop. And most chose a top read story in this category where the chiplet IP standards are just the beginning. Data and protocol interoperability standards are needed for the EDA tools as there are more hurdles ahead. Customized chiplet will be required for AI applications. This was part of the exposed at the table series. Chiplet cannot exist without a interposer, and the industry is still grappling with the 2.5D integration, big chip or small PCB. I tackled the issues of whether the 2.5 device's printed circuit board shrink down to fit into a package, or is it a chip that extends beyond the limit of the single die? While they seem to be a thing like hair-splitting semantics, and it can significant consequences for the overall success of a design. Another aspect at the table series look at defining the chiplet socket and what comes after HBM4 chiplet. The industry may have started the wrong approach for enabling the party chiplet economy, but who will step in and fix it? This was a lively discussion that brought together ideas from the system foundry, EDA, interconnected companies. Some memory. While memory makes seem like a sleepy backwater, it is an area that is hitting all kinds of limitations. That means advances are more likely to be out of the box. Karen Heyman conducted an expert discussion that looked at the future of the memory. From the attempt to resolve thermal and power issues to the role of the CLS and the UCIA, the future holds a number of opportunities for memory. She also tackles the issues of the SRAM scaling issues and what comes next. The inability of the SRAM to scale has a challenge to power and performance goals, forcing the design economists to come up with the strategies that range from the hardware innovation to rethinking design layout. At the same time, despite the age of the initial design and its current scaling, the limitation in SRAM has become the workforce memory for AI. Corresponding the instance of this area, the semiconductor engineering released ebook is a memory fundamental for beginners. Nearly everything you need to know about memory. That includes a detailed explanation of the different types of memory, how and where these are used today, what changes to which memories are successful and which ones might be in the future, and the limitations of each memory type. So Happy New Year. Well, it's a wrap of 2024. Thanks to everyone who has contributed to all of the stories we have prepared this year. Without you, none of it would be possible. And it is you who make us look good. Well, maybe good is a stretch. Looking forward to another exciting year in 2025, which might have many surprises in store for all of us. Okay, this is and the articles. The wearing software for shift left. Shift left requires the abstraction on which early analysis can be performed. For architectural analysis, abstraction are required for both hardware and software. Co-development of the hardware and software has been a dream for a long time, but significantly hurdles remain. Neither domain is ready with what other requires at the appropriate times. The earlier one thing can be done in a development flow, the less likely as problems will be found as they are more difficult and expensive to fix. It may require both tool and methodology changes, though that the process step has been necessary information earlier, and tools estimate the impact of the potential changes. This generally is referred to as shift left, and it is prevented significantly challenges when it comes to hardware and software code design and integration. Software integration traditionally happened after the first silicon was available, but there is a desire for to be undone pre-silicon. Performing this operation post-silicon can lead us to surprises, but at that point it's too late to modify hardware. The result is a costly software modification, which can significantly impact time to market, performance, and power. This doesn't always mean the production software must be available during hardware development. It may be possible to define the realistic software workload so the hardware architecture can be optimized. Software from the previous product or prototype software may exist, and while this isn't necessarily the same software that ultimately will run on the hardware, it could be helpful for many hardware design tasks. This could include identifying traffic congestion or peak power so that the power delivery network can be properly designed. In other cases, the real software already exists and the hardware is being designed specifically to accelerate that function. For example, video encoding is a highly important task for streaming services. Power saved performing this task can lead to a substantial efficiency gains in the case of the hardware for AI/ML. Not only is software available for hardware, but it is almost certain that the software will help advance significantly by the time that hardware is ready. All of these are causing the companies to reassess their methodologies associated with hardware and software development and integration. An increasing number of tools are becoming available to help with, but in some senses, tool development suffers from the same problems. Hardware tool developers and software tool developers tend to be different companies, and they have yet to come together to solve some of these problems. When either software or hardware comes first, ways are needed to bring them together virtually. So the way to get things earlier is abstracting. Say Marcus Serugeti, Vice President of Product Management of Applications Engineering and Software. It's no difficult than the other domains you are abstracting because you can get to the information early without knowing everything. The disadvantage of abstracting is you are removing information, and if that information ends up having an impact, you are losing the piece. And that's why these approaches can only work if you have a methodology that looks at it as being iterative and many milestones along the way. So, availability of the software. There are many types of software and each has to be considered separately. Associated with microcoder Jeff Rohn, Director of Product Management and Marketing at Cadence. This is software that's developed by the semiconductor vendor, and it won't be modified by the end of customer. Application code rarely exists before the SoC is designed, with the exception of end-user application code. The Android Software Development Kit (SDK) and iOS SDK are examples of those, and they've got the whole world developing application apps, and it is their job to make sure their SoCs are 100% compatible with the body of work, the legacy work, and the new development that's taking place. It's that the application code for a new SoC where there is a chicken and egg problem. So this is a multi-pronged strategy often is required. So the software and hardware code design is often practiced, in which both software and hardware evolve iteratively, said Andy Nightingale, Vice President of the Product Management and Marketing and Artists. The collaboration between the hardware and software teams ensures that the software is ready or adaptable by the time the hardware is finalized. In many cases, early-stage code bases the focus on a core functionality can be made available. Alternatively, test software can be designed to mimic realistic workloads and benchmarks. There are other approaches being taken by some industry. Within the automotive industry, they are trying to separate software to make it independent of the hardware, said Synopsys Setugeti. There's always will be some software that will be dependent on hardware, but you can start in separating those pieces. Shift left start by asking what can be done to start developing the application software independently of the hardware. For lower level software, it is hard to start developing it without the hardware. This is where the concept of virtual prototyping are playing a role. One of the concepts in Shift Left is to avoid Big Bang integration, that the two things come together. As you go toward this continuously iterative process of software development or validation of the verification, you start validating and verifying around different aspects. The earlier in the integration can start, the more valuable it becomes. Shifting left and having things available in a software development allows the system designers or system architect to be able to anticipate problems earlier, said Lishi Kamdar, Senior Director and Portfolio Manager for the RF and Microwave and Power Electronics and Device Modeling EDA businesses at Keysight. There may still be things the escape where an issue gets observed much later on, but the opportunity exists for a lot of things to be addressed and found much earlier. So for wireless communication, their code developed while the hardware is developed. It does not always get completely finished with code developed continuing later, but a lot of these happens earlier. In other industries, the alignment is not yet in place. The ability of the software during the design phase remains a major issue, said Andy Heineck, head of the Efficient Electronics and Fraunhofer's IIS engineering of the Adaptive System Division. The purpose of the digital twin is to develop the software in parallel and with both the design and manufacturing processes. However, often only software for the old generation of hardware is available, which serves as a starting point but does not consider new features and requirements. The ultimate goal is to be able to have hardware and software influence each other so that the best solutions can be deployed. This means making the abstractions of the hardware available earlier for software development and establishing software development practices that enable the important pieces of software to be available early in the hardware development. Hardware for software development, there is no solution that provides a perfect solution. As the all forms of abstraction, you either give up the accuracy, visibility, or performance. What's needed is a combination of cloud-native simulation and its extensive model library, integrated tool chains, and a hybrid virtual RTL environment, creating a highly efficient and effective ecosystem for modern hardware and software development, says Jeff Hancock, a senior product manager at Siemens EDA. It includes merging the virtual and hybrid models together. This holistic approach not only accelerates the development process, but also enhances the quality of the performance of final product. It allows your software team to get started months or possibly even years ahead of where they would have in the past. This helps customers get to market faster and with better quality. The virtualization can provide highest performance in the automotive industry, and SOAFI, a collaboration involving more than 140 members in the automotive and software ecosystem, has worked to be defined architecture to support in the cloud development using modern virtualization technologies, said Robert said, directors of automotive go-to-market in North America to ARM. It enables a seamless development to be vehicles, and this approach allows automakers to support the same software across different hardware platforms to ensure that software can be tested before the hardware is available. So the many hardware development teams start by defining a hardware high level. By defining a high-level model. If we have a virtual models or digital twin, you have a high-speed model that is written in C++, and you can solve some levels of the software development on it. Set the cadence is wrong. It comes down to how fast you can simulate enough patterns to do anything meaningful. So the applications that manipulate images or auto stream tend to take millions of cycles. So you get a point that where you can only do so much. Even you are developing a C models, those models aren't fast enough to do any meaningful software development. So that only enables you have confidence in functional correctness. Another solution is mapping the design to an FPGA alone. That can run north of the megahertz. The challenge is that you have a design that really targeted for a ASIC and IC process node. Then the mapping to an FPGA is a completely new, different design, and because now you are mapping the different structures, complex logic blocks as opposed to base level cells, the timing is completely different, and you got to redesign that whole things just to put into an FPGA. So additionally, mapping the FPGA can limit visibility. For enhancing the visibility or meaningful number of performance and power, you are going to need the actual RTL that runs on emulator such as Getty. This can be slower. Then you ask if I really need to have the ARM processor in the emulator. I could put this in a virtual platform. The hybrid world enables you look at your development process as being iterative as software grows. It also enables you to cut the problem into pieces. When people talk about the shift left, there are two elements. One is starting earlier. The other is ability to do it with piecemeal. To bring up an operating system, you don't need a full SoC doing a driver for GPU. You just need the GPU and maybe some host core on other side. So the other side to this is what hardware can provide to enable software to be more aware of things like performance and power. As I don't know that is being done yet, said Ron. At what stage is feedback being given to the software developed from the hardware consumption characteristics of the device that they are developing software for? The software developers interact with the debugger that provide a purely functional view. They are not used to looking at a hardware structure, and they are not used to looking at a power consumption profiles for those hardware structures. There is a team approach when it comes to resolving the issue. The software developer is still focuses on functionality and also performance of that functionality, but when it comes to optimizing for power, it's still the hardware team. This is where the value of service like continuous integration and continuous deployment to provide value. They enable the developers manage continuously evolving software workloads at the ARM stage. The CI/CD pipelines help track software and change and ensure they do not negatively impact performance or power consumption. This service can provide automated testing and deployment and maintain the integrity of software throughout the life cycle of both software and vehicle. CI/CD provides a value of a feedback loop by regularly integrating software changes into tested environment. You can access the impact on the performance and power, said artist Nightingale. Regression can identify the changes against the established baseline. This provides an important guide to software development, ensuring it aligns with the hardware constraint. What is important is that you understand the objective for each solution. There is no silver bullet, no panacea is where you can model everything. Create create a virtual twin that will run at the gigahertz speed and give you complete visibility into everything that run. These are all solutions that you can part way down the path. But there's a reason why you are designing that silicon. That's the things that will give you enough juice to run everything. Yeah. Software and hardware development. Different levels of software need to be available for each hardware development task. At the architecture exploration phase, you can often use a software that are represented by your previous generation Getty. Alternatively, software can be represented by a task graph. This is not the actual functional behavior of the software, but a representation of the events that are happening in the software. Where you are trying to do is optimize your interconnect. You are trying to optimize memories, and for this you don't need all of the software. Okay. When it comes to power optimization, more accurate representation of software are required. If you want to do the more power optimization, you have to optimize in Fourier or real workload, which means you have to go to the software team that run. In the past, people tried to develop vectors that represented those meaningful workloads. Given the amount of software and how critical it is far better just to go to the source code, a source of those workloads, and much more realistic than any test of an SS designer would to wiggle the gates in the design. Does designer connect? I'm not sure. It's important for teams to continuously assess their processes to work out if better solutions may exist. If you go back 10 years, electromagnetic simulations were very expensive in terms of compute times. Say Keysight, COMDAR, you could only run them on a single computer and take up all the memory. This impacted the pace at which hardware decisions were made, and it impacted the accuracy that designers had to live with. Became multi-threaded CPUs, hyper-threaded options, and became massively parallel compute options, and instantly you are able to get answered faster. Now you have more predictive ways to do hardware design. It makes you realize that previously you were cutting down the problem something that you could manage, and now you can handle the bigger problem. Today, the many problems that have to be cut down to remain manageable. If you have a workload, it probably spans billions of cycles that run. You are not going to through the billions of cycles that optimization engine and say, optimize for this workload. There are enough time. These challenges become how to pick a meaningful subset of of data software and use to go drive optimization. What you are doing is saying, I'm going to design my power supply and a power grid as specifically to accommodate this worst case. This is only with a subset. The process, that is the process first. One thing is clear, as this is primary methodology issue. The big bang that used to happen when software and hardware becoming together is no longer viable. An iterative approach is required where both the hardware and software team have to coordinate to ensure that each is meeting the needs of the others. It all starts with the specification. The virtual prototype is a representation of something. Said Getty, even just a few years ago, most companies didn't have a written specification. It was very hard to get started on the virtual prototype. Each process problems when a specification is written only once something is available. Many companies decided they needed to have better specification up front. That doesn't mean the specification is fully right, but the advantage of having a virtual prototype is that I can validate if the specification is correct. There are assumptions being made in the specification, but how do I validate they are Right, with the virtual prototype, the first phase is actually clarifying the specification and ensuring a common understanding between the hardware and software folks and person who wrote the specification. This is a real problem and one needs to be addressed. The solution involves methodology along with tools and techniques available to this. It is also necessary for the makers of tools to start working closer with their counterpart companies because the solution being provided today to not to fully address the issues. Okay, it's quite a long paper and long articles. Thank you for your time. See you next time.